97. Answer the following questions. And then we have letter H. In this one it says a balloon flight can last about 90 minutes. If all of the fuel is burned during this time, what is the approximate rate of heat loss in kilojoules per minute from the hot air in the bag during the flight? Okie dokie. So when it comes down to it, all they're asking for is the approximate rate of heat loss. Now, for this one, I mean, it's letter H, so it's gotta be a little bit tricky, right? So I want to kind of give you a heads up, if we're a shot in the dark here. All they're asking for is the approximate rate of heat loss, right? And they gave us the units. Always use the units to help you out. Literally, all we have to do, right? I mean but basically, essentially, all we have to do is just find a kilojoule. Whoa, what happened there? Just find a kilojoule value, right? kJ, and divide it by a minute. Always look at the units because then you can kind of make your own equation. All we have to do is just get a kilojoule unit and divide it by a minute. Let's see. Do I have a kilojoule number? No, they didn't give me a kilojoule number, but they did give me the minutes already. They did tell me that balloon flight lasted 90 minutes. And what's the approximate rate of heat loss during this time? So I already know half the battle. I know that whatever the kilojoule number is, I have to divide it by 90. But now the whole thing is, for this question, is what is that kilojoule value? Well, here's the thing. I brought in everything that we have already done from parts A up until H here. Majoritively, it's coming from the last question, which was letter G. So if you need to go back for a refresher, go back to G. But we did the balanced equation there, so I'm pulling that in. We talked about how propane, they told us that there was 40 total gallons. So that equals 151.416 liters. We did that conversion. Also, they told us that the density of the propane was 0.5005. So this is all coming from the last question that we did and the balanced equation. Now, they did say that if all the fuel, and remember the fuel in this case is the propane, right? It's the liquid propane that we talked about in the last question. That's C3H8, that's this guy. So if all of it was burned, that means that all of these liters, all of the 151, and maybe I'll do it in a different color, all the 151.416 liters is used, right? But how am I going to get a liter value in terms of a kilojoule? Because remember, this is essentially what we're trying to solve for. That's where another chapter comes in. Kilojoule, remember, is enthalpy. And enthalpy values are found in the back of the chapter. So what I did for you guys is I went to the back of the chapter and I found out all of the standard values for each a compound or molecule here, because that's how we're going to find a kilojoule value, kJ. That comes from enthalpy, which I believe was enthalpy, I think it was thermochemistry chapter 5. I believe so. But it comes down to this one formula, and we've seen it time and time again. It's this one right here, right? Products minus reactants. So all we have to do is basically to find out that total heat of reaction. Remember, delta H is enthalpy, or a fancy way of just saying how much heat is being produced. All we have to do is just find the sum. That's what this little thing is. The sum of the products minus the sum of the delta H's of the reactants. So in essence, it's products minus reactants, the sum of them. So let's just write down the numbers first. So I color code them. I'm going to put the blues over here. So I got negative 103.85. O2 was a 0. And remember, all these numbers are coming from the back of the, your text. You are not required to memorize these random numbers. But just know that any molecule by itself has a delta H of 0. And this would be negative 241.82. Now remember, it's the sum. So we have to add all the blues up and add all the reds up, but there's a catch. For some of them, you have multiple of the compound. In this case, we have 3 CO2s. These numbers are if you only had 1 CO2. So if you have 3 of them, I have to multiply this by 3. And then since I have 4 H2Os, I got to multiply this by 4. And technically, in theory, I have 5 O2s, so I have to multiply the 0 by 5. And there was no number in front of the propane. That just means 1. So you can multiply this by 1, but, you know, we could leave it alone. Now, since it's literally addition, that's when you add the sums up. So, the reactant side is easy. If I add these two numbers together in the calculator, it would just be negative 103.85. Light FM, KTU. I don't know. Do I have a radio voice? No. Okay, now I'm going to do the product. So 3 times negative 393.51 plus 4 times negative 241.82. Okay, cool. And this comes out to be negative 2147.81. Or in my Siri voice, 2147. Anyway, I'm having too much fun. Okay. So now we're just going to plug it in here. Delta H for the whole reaction. So how much heat is going to be produced is products minus reactants. Negative 2147.81 minus negative 103.85. So let's see, what's my delta H? So I'm just going to plug that in. This number minus a negative 103.85. So I get negative 2,043.96. Whoa, okay. Now, here's the thing, guys. If we're just taking it from the table, the delta H value is kilojoule per mole. So this is technically kilojoule per mole. But remember, not most of you, but some of you might say, oh, I got my kilojoule. I'm going to plug it into here now. There was no mole value here. This was just kilojoules. This is in per mole, right? And in essence, if we find the one that we care about, right, we care about the fuel. So in this case, how many moles of the the C3H8? Yeah, there was only 1 in front of here. So technically, this would be kilojoules per 1 mole of C3H8. But now the thing here, guys, is do we have exactly 1 mole of C3H8? I don't think so. I don't believe that 40 gallons, aka 151.416 liters, is exactly 1 mole of C3H8. We have to find out how many moles do we really have from 151.416 liters. So the first thing is that pause the video if you need to write some of this stuff down, but some of this has to go because we got to do more math. So I'm going to just get rid of all of this. We don't need the delta H's anymore. Goodbye. And this, for now, will nicely sit. We'll put it right down here. It's going to come back later. But now remember that we started off with 151.416 liters. And the question is, I want to find out how many moles this is. Well, they gave me a volume. They gave me a density. Remember the formula, D equals M over V. If I have the density value of 0.5005 and my volume is 151.416, I can solve for the mass, right? And if I just quickly manipulate this formula to just solve for mass, it would be M equals D times V. So I can just times these two values together. And I just do a quick check just to make sure that the volume liters are the same, but this one is per liter and this is per liter as well. So we're good. So in this case, I can go from liter to grams, We're getting there. We're getting there. We need moles, but we're getting there. So let's figure that out. Mass equals the density, 0.5005. When I do my math, I don't like to put in units because I just checked before, and then I know that I have the right units. Okay. So mass is 0.5005 times 151.416. This, again, is also not the final answer, so I'm not going to care about sig figs. But this is roughly about 75.784, we'll say, grams of the C3H8. So we're getting there. So this, if I just move this out, this is the same thing as 75.784 grams. Well, now what's the next thing? I gotta go from grams to moles. This we've seen time and time again, right? Grams to moles, we could do the conversion. An easy way is just dividing that number by the molar mass, mm, right? Found it on the periodic table. But if you want to do the quick conversion, remember, it's 75.784 grams of, in this case, it's the propane, that's the fuel, times by that ratio. Since you don't want the grams of C3H8, that goes on the opposite side. So grams of C3H8 go on the bottom. And then the mole of C3H8 go on the top. Remember, periodic table, 1 mole equals the molar mass. So in essence, all you're doing is just dividing by it. So let's just figure out what that is. 3 times 12.01 plus 8 times 1.008. So I get 44.094. Grams cancel. Let's find out that number. 75.784 divided by 44.094. I get a total of 1.7, we'll say 1.719. And that's moles now of the C3H8. All right, we're almost there. Now, if we just go back, right? Remember, 2,043 kilojoules of heat is going to be released per every 1 mole. If we had to just kind of check ourselves here, we have more than 1 mole. So would this number be, a greater amount of heat lost or a smaller amount? It would be a greater amount. Forget the negative. Just look at this number. It would be more than 2,000. Remember, the negative just means that the heat was lost. It does not specifically say that you have a negative amount of heat. This just means that it was lost in the surroundings. So you're releasing it. So now all we just got to do is just bring these two together. So pause the video because actually what I'm going to do is I'm just going to bring this out. I'm just going to state that again. So this was 1.719 moles of the propane. And now I'm just going to get rid of this. Okie dokie. So now we're going to bring in this number again, right? Now, you don't have to really bring in the negative. Remember, the negative just means that the heat was lost. It's not an actual negative value. And since they said, what is the approximate rate of heat loss? It's already assumed that that number is going to be negative. So you don't have to say it again. So I'm just going to keep the positive from now on. So this would be 2,443.96 kilojoules per 1 mole of C3H8. And now since we have this amount, all I have to do is just times it by that number. Because what's going to happen to the unit moles, guys? It's literally the same unit, moles of C3H8. Yeah, you're absolutely correct. They go bye-bye. Whoop, whoop. And that's how you just have kilojoules. See, this is the only number that is still hanging out. So all we got to do is 2,043.96 times this number. Let's get it. So 2,043.96 times 1.719. 1.719. Okay. And it kind of makes sense. We do have more. So we're on the right track. 3,000 513 point, we'll say 57. Still not the right, the final answer, so I'm just going to hold it for there. So that's that. And now we know the kilojoules. The kilojoules are 3,513.57 kilojoules. And now let's just do that math. So 3,513.57 kilojoules divided by the 90 minutes, because we knew that number all the way from the beginning. This equals, I'll just put the answer over here. Let's see. Doing the calculator, 3,513.57 divided by 90 is 3 sig figs now, because it all stemmed from the gallons. We can call it that. At this point, who cares about sig figs, right? So 39.0. And that's kilojoules per mole. 39.0. So that means, not kilojoules per mole, that's like an instinct. Kilojoule per minute. So that means for every 1 minute, the propane as the fuel is releasing 39 kilojoules of heat. And then in 2 minutes, it would be 39 plus 39. And then in 3 minutes, you would just times this by 3. Up all the way up until 90 minutes to get the full 3,513 kilojoules. But that's it, guys. This question is finally done. I really hope this helped. Let me know in the comments. Subscribe to the channel. Thank you so much. Tell your friends, tell your classmates that, this cool, YouTube channel exists. All we want to do is help you guys out. We got math and physics videos also on the channel at the moment, but we have such, a bigger plan for the channel. So my brother and I, we've been tutoring all different types of subjects. So we want to help you out, all right? So I will see you all in later lessons. Bye-bye.